limitations are that these are not in relative states. So if landmarks are not present, the system becomes inherently unobservable. And you need relative positions for doing close coordination and control. So you have to transform this problem to relative space and then solve this problem. Okay. So that is the kind of missing parts in the cooperation here. So there are two missing parts here. One is missing things with relative thing. That is in 2D, unobservability problem, accuracy problem. But then again you go to cooperation stuff. Cooperation is not solved in relative frame. Okay, and it is unobservable. You need landmarks. Okay, so now we are trying to combine relative localization with cooperative localization, and then propose a method which is kind of limits or addresses all these challenges existing in both relative localization and cooperative localization problem. Okay, so that's there. And so the next slide is basically now you come to the contribution of this work. Okay, this is what this work is about. So you can so this slide and this slide you can combine together. Maybe in one you can use two columns, right? The ship is here.
Change the notation, right? 0, 1, 2, 3.
Yeah, so I use this one. Is this correct? Yeah, this is correct, I think. Yeah. So we are saying that the vehicle that is landing is 0.
Yeah.
Okay,
and then the ship is 3.
Ship is 3. So that is the idea, that the vehicle that lands is 0 and the ship is 3. And so I've changed the notation. Yeah. Okay. So this figure and then maybe the contribution. So the main contribution is that you're trying to land a vehicle on a moving platform, something like a ship, and the idea is to do the 3D relative pose and heading estimation, and then develop a cooperative relative estimation problem. You develop a controller that uses those relative states to land the vehicle on the moving platform, and then so that is the kind of problem that you will be that is the main contribution of this work. Okay. So then you go to equations of motion. Before equations of motion, you can say that each vehicle is equipped with a IMU and a range sensor. Okay. So IMU and range sensor. So range sensor can measure range between quadrotors and the ship. So basically, this vehicle can measure range to all the quadrotors and ship, as well as the other vehicles. Okay. So they have the same. Everybody has the same sensor. Ship has an IMU as well, and that IMU you can use to get your velocity, both the linear and angular velocities. I will come to those when we talk about equations. And also you can get phi and theta, that is the attitude of the aircraft or the ship. Okay, you can all so that is the idea here. So the equations of motion, maybe you can put a picture of a quadrotor and a ship and then show these phi, theta, psi, x's and all that stuff. Okay, so this is the equation of motion of a quadcopter, and the first equation is the linear velocity in inertial frame, which is this vi is the body frame velocity, and then you have this body frame acceleration vi dot, which is given by this equation, where phi and theta are the roll and pitch angles of the aircraft. Ti is the torque, and then this is how the phi dot, theta dot, psi dot is related to the angular velocity. This omega is the angular velocity of the aircraft, which is measured using a gyro, and this is the angular acceleration. And these T phi I, T theta I, T psi are the different torques that are generated by motors, the rotors on the quadcopter. Okay. So after this, you can put a basically this figure, just this figure 3. You know, this one here, that just that every these days quadrotors have autopilots, and because of the autopilot, they have internal velocity and attitude control. So all we do is send a velocity command to the quadrotor, and the internal velocity and attitude controller basically generates these torque and thrust commands to move the quadcopter. Okay, so then you can work on the reduced state. Maybe you want to include that slide that says that the states that we will work will be the position pi dot and the psi I dot. Okay, so 4 equations. These are 3 equations. It's a 3-dimensional vector, and then the 4th equation is the psi I dot. So total 4 equations is what you will be using. So total 4 states. Reduced state is basically 4 states: north, east, down, and your turn rate. Okay, and your input is the body frame velocity vi, and which can be seen in this figure. So in this figure you can see that the input to the system is vi and ri. These are body frame velocities and turn rate, and then this internal velocity and attitude controller generates the torque and thrust commands, which is then sent to the quadcopter. Okay, so our reduced states then become just the position and the turn rate. Okay, so now we want to derive the relative position. So we are not interested in northeast down position. We are interested in how far the other vehicle or the ship is in with respect to the landing vehicle. Okay, so that is what we are interested in. So what we do here in equation 5 is first we find the relative position between two vehicles, between PJ and I. So between PJ and vehicle J and vehicle I. In this case it can be vehicle J can be 1 and I can be 0. So between vehicle 1 and vehicle 0. So this, with the quantity within the bracket here, is the relative position in inertial frame. Okay, then you can take this position which is in inertial frame to vehicle I's frame by multiplying this rotation matrix, okay, RIT, which depends on the attitude v theta psi of the ith vehicle. And so these are again 3 equations only. The PJI is the relative position between vehicle J and I in vehicle I's frame. That is the notation what we are using here. Okay, so this is a 3-dimensional vector. Equation number 5 is a 3-dimensional vector. Now this is relative position in vehicle I's frame, and psi ji is relative heading, which is simple, no rotation required, but difference between psi j and psi I. So these are the 4 states that you are interested in from now onwards. Okay, so that is the idea that and so now you want to find the equations of motion in relative frame. You had in previous slide equations of motion in inertial frame. Here this equation 1 and psi I dot gives you in inertial frame, but now you want to derive pji dot and psi ij dot. Basically just take differentiate with respect to time from both sides, equation 5 and 6. So maybe I should write 5 and 6 here. Okay, so I can, after doing some manipulations, I will get this equation number 7. Okay, again this is a 3-dimensional equation here. Okay, and this SIT is your skew schematic matrix, which again depends on the angular velocities measured using a gyro. Okay, see this is available. So these are the equation number 7 that you get, where RJI is the rotation matrix from vehicle J to I. Okay, and which is derived as follows. It's simply you plug in the value of Ri and Rj, and then if you do calculation, this part here becomes R psi ij, which because we don't have individual psi I and psi j. We have individual phi and theta estimates, but we don't have individual psi I and psi j. So when you multiply this, you get an equation called R psi ij, which only depends on the relative heading. Okay, so this is the matrix it depends on this delta psi ji, which is basically a state here. Okay. So equation number 8, and this phi and theta is estimated using IMU for each vehicle, and which is kind of broadcasted to the landing vehicle. Okay. Any questions so far?
No.
Well, you can play this video and read the paper, and then we'll go from there. Okay, so now we come to cooperative localization problem. So the cooperative localization problem is, I think you are basically doing a joint state estimation. Okay, and joint state estimation, you are defining the states xi. Basically, I call it I, that I represents in which vehicle's frame. Okay, so in this case I equals to 0, if you see. Okay, so basically I can write 0 here too. Okay, so we are estimating x10. What does x10 means? Quadrotor 1's relative position in vehicle 0's frame. Right, so 4 states. This is 4 states. So 4 states. So if we have total 4 vehicles, so vehicle 0 is estimating for 1 and 2 and 3. So total 12 states. That is what we are going to estimate here, right? In cooperative localization. So each x010, x20, x30, x10, x20, x30, and each has 4 states in it. So total 12 states is what we are going to estimate. Okay, and the range measurement between any two vehicles is given by this equation here. Okay, you don't need any inertial information here. Everything is so if you explain this block, so this is a quadcopter which has an autopilot here. So the velocity in body frame and turn rates are given, and it generates thrust and torques. And then it has sensors like an IMU and range sensor, which measures range between
Attitude
vehicles.
and velocity.
And then IMU is used to estimate this phi I and theta I. And also VI is the linear velocity, and omega is your angular velocity in body frame. So everything is in body frame here. So you receive, so vehicle 0 receives its own sensor data and also receives Vj, omega j, phi j, theta j from other vehicles. Okay, and then you just put all that information in here and estimate, do sensor fusion and estimate relative position of all the other vehicles in vehicle ice frame or okay. So it is estimating these 12 states here, xi here, which then goes to a controller. So the vehicle landing does not need